Another set of identities that we're asked to use is the half-angle identities. In this video, I'm going to prove all of the half-angle identities that they give us here. And the trick is by replacing theta with theta over half, you can use your power reducing. So really what I'm going to do is I'm going to try to establish the fact that the sine of theta halves is going to have to equal plus or minus the square root of 1 minus the cosine of theta all over 2. So as in all of the proofs that we've done, if we just get these put in the right format, then we can use some identities that we already learned how to do. And here's what we do with this problem. What we do is we rewrite theta as 2 over 1 times theta over 2, all over 2. Now in essence what I've done is I've really multiplied this times 1, because 2 divided by 2 is 1, and we still be left with theta. So that's an equivalent form. The next thing we're going to do is we're going to let x equal theta over 2, so that I can replace that in that equation. So that's going to help clean up this equation a little bit. So we're going to have it's equal to plus or minus the square root of 1 minus the cosine of, since we're going to let theta equal, or x equal theta over 2, it becomes 2 times x all over 2. Then, if you go back to your power reducing formulas, if you look carefully at that, this 1 minus 2 cosine of, or cosine of 2 theta divided by 2, that is the same thing as the sine squared of theta. So what I'm going to do is I'm going to replace this whole thing sitting right underneath here. That is equivalent to the sine squared of, in this case it's x because that's our variable. So that becomes plus or minus the square root of sine squared of x. And now what we're going to do is we're going to take the square root of sine squared. Because it's a sine squared, I don't have to worry about this being negative. So this negative gets tossed out because sine squared, no matter what we do, we're going to square our value, which makes it positive. So we'll be left with only the positive root of square root of sine squared, which is just sine of x. So that's the proof for that. Now, as in the other videos, I've proven the cosine one as well, but I'm going to stop short at that. I'm going to let you look at this for the cosine derivation of it, so you got that one there to fall back on. Next thing I'm going to do is I'm going to try to verify that the tangent of pi halves, the half-angle identity formula for tangent, is plus or minus the square root of 1 minus the cosine of theta all over 1 plus cosine of theta. If you follow along what I did in the last example with the sine of pi halves, and you looked at this one that they had for the half-angle identity for cosine, what you know that you're going to do is you're going to replace your thetas with an equivalent form, so plus or minus. Wherever you have thetas, you want to rewrite those as 2 over 1 times theta over 2. Same thing on this one, so it's 1 plus cosine of 2 over 1 times theta over 2. And again, your let statement says let x equal theta over 2. That way we can fall back on our double angle identities or our power reducing identities. So we got the square root of, this is 1 minus the cosine of 2x all over 1 plus the cosine of 2x. Now this, sitting underneath the radical, should be an equivalent form of the power reducing identity for tangent. So what we're going to do is we're going to replace this with plus or minus the square root of the tangent squared of alpha. And just as we had in the previous derivation, since it's squared, we don't have to worry about the negative, so it's only the positive tangent of x. I don't know why I came up with an alpha here, but tangent squared of x, and that'll be plus a tangent of x. And remember that x represented, and now that I do this, I'm not sure if I did it last time, substitute back in theta halves. So it is equivalent to our tangent of theta halves. Now there's other versions of this tangent one. I'm going to show you just one derivation of that, and I'm going to take this, the next one in line, and you can derive the other one in a similar fashion, but it's theta over 2 equals 1 minus cosine of theta all over sine of theta. Okay, so as we've done in the other examples, what we're going to do is we're going to have an equivalent way of writing theta, so we're going to replace those with 1 minus the cosine of, this is 2 over 1 times theta over 2 over 1 sine of 2 over 1 times theta over 2. So this is a 2. That's a messy 2, so let me try to clean it up. Nothing worse than lousy writing on these. So this is sine of, taking it times 2 over 1 times, and this is theta all over 2. So it's still equivalent, and we're still letting x equal theta divided by 2. So now we're going to make our substitution or replacements with 1 minus the cosine of. Our 2 stays in place, but theta over 2 is equal to x all over. This is the sine of, it's going to be 2 times x. Okay, now what we're going to utilize in this one is our double angle identities. So it's 1 minus the cosine of, a double angle identity is cosine squared of x minus sine squared of x. You saw me sneak the brackets in there because it's got to be 1 minus the quantity, and I'm making a substitution for a double angle, which has 3 different versions. I just chose this version. And then sine of 2x, so that's going to be the 2 times the sine of x times the cosine of x. And then we're going to make a substitution, or at least I have a choice of what order I want to go in. So I guess the first thing I'm going to do is I'm going to distribute the negative. So it's going to be 1 minus the cosine squared of x, then plus sine squared of x all over 2 sine of x times the cosine of x. Keeping in mind, we want to try to get this to look like a tangent, and tangents are always sines of x over cosines of x. So I'd really like to get this cosine out of there. So this is where we can apply one of our Pythagorean identities. So get rid of the cosine squared, and it's 1 minus sine squared of x plus another sine squared of x all over 2 times the sine of x cosine of x. We're going to distribute our negative, so it's 1 minus 1 plus sine squared of x plus another sine squared of x all over 2 sine of x cosine of x. And then we'll gather our like terms. Those will reduce. Sine squared of x and sine squared of x is 2 sine squared of x all over a 2 sine of x cosine of x. If we apply that, then what we have is the 2's will reduce, one of the sine of x's will reduce, and you'll have a sine of x over the cosine of x. Got one more thing to do. What did x represent? We go back to our left statement, and that meant x was theta divided by 2, and the cosine of theta divided by 2. And this is another representation of the tangent of theta halves. So that's a derivative or a proof of that identity. Like I said, that leaves us one identity short, and I'm not going to do that last one, but I wanted to show you the connection between the tangents and the sine.